Let's go ahead and get started. Welcome back. Yeah, good. So this time, now that we've gone through some of the basic cryptographic techniques, we're going to start looking at actual, how we store information. And the most common way we store information in computing systems is through databases of some form or other. Of course, if this slide was really updated, I would call it blockchain security because blockchain is just the new database. But we'll just talk about databases again for now. So we'll first talk about kind of the system aspects of how we manage databases in a larger computing environment, how they're typically used, and then go into a number of attacks that are types of attacks that are particularly common against databases and information stored in databases. And then we'll talk about some practices and techniques for managing sensitive databases, especially both in general for general databases, but also looking into one for a particularly common important case, which is managing credential databases, things like password databases, which are super common on servers and a very, very common target of hacking attacks because they let attackers get into many other systems if they compromise a password database. So, okay, so basic introduction. Well, databases are used everywhere in every industry, but we need to carefully consider the security of the databases and the data they contain and the different attack vectors and ways we can protect them. So there's two main standard ways to view databases as they tend to exist in the internet connected world. Pretty much it's hard to find databases these days that aren't at least indirectly somehow connected to the internet, because it's just so useful to have electronic systems be able to access databases, and they're needed for so many things online. If you had the data, you could always the ultimate security is just leave it offline entirely in a sealed box or vault, a physical vault somewhere, but it's not that useful that way. So usually most of the databases that are of interest are at least indirectly connected online, but standard practice is to typically put them either, of course, behind a corporate firewall, sometimes several levels of firewalls, depending on the network organization and practices. And they're usually, in some sense, sitting behind and supporting some other front-end server logic as well, such as the web servers that are actually serving requests to users and clients. So this is a very common picture of how databases tend to be connected to the internet. Now, it's the era of cloud computing. Cloud computing is becoming increasingly common and popular as well. This is kind of another word for tech outsourcing, basically. Just many companies just say, okay, we don't want to manage our own databases. We don't want to manage our own servers. So they outsource that to Amazon or Microsoft or IBM. And in this case, it's often the case that both the databases and related servers like web servers and logic sits in the cloud somewhere, running on behalf of the company. So a very common way these things are deployed is what's called the multi-tier architecture. The most common is basically to look at this as 3 tiers. The way especially most web accessible services work, things like online shopping carts, or banking, insurance services, all kinds of things. Of course, there are plenty of variations, but this is kind of the basic model. So the data, on disk or in persistent storage sits in the data tier on a database like, or Oracle, or some other SQL database. And then above that, sometimes on the same server, but often on separate, physically separate servers, is a logic tier, which implements what they call the business logic. Like, if we're talking about a company that's like IKEA that lets you order stuff online. So this is where the logic will sit that determines how your shopping cart works. Kind of what it means to to browse the inventory and put an item in the shopping cart and check out and stuff like that. That's typically the logic tier, which handles the actual business logic. And whenever it needs to decides to change anything in the state of the system, it sends a query, very often in SQL, the structured query language, to the database server saying, okay, please write this transaction to the database, or do this read to check the contents of the shopping cart or the contents of the inventory, or things like that. And then at the top tier, we have the presentation tier. This is where basically the user interface logic sits. Where we have code both on the server side and code that's shipped to the client side in the form of JavaScript, often to implement nice, friendly user interfaces that make everything look nice. But an important point is the presentation tier especially, and the logic tier in general, is often more or less designed to be more or less stateless in that all of the real state, persistent state that matters is generally stored in the data tier in the databases, and the stuff up above just accesses it, just kind of submits requests to the lower tiers to figure out, well, what's the current state of the system, and based on that current state, we can support these operations and stuff. So that's just a general, a lot of details differ. That's just a general reference model, but we'll come back to that, and it's important to understand that general model in order to understand how many hacks work and how both good and bad security often works around databases. So there's a lot of different types of threats to databases and the data they contain. Many of them attacks just that exploit misconfigurations of the database in various ways. So when their databases are configured so that certain accounts have too much privilege or unnecessary access that an attacker can exploit. Weak passwords on accounts. We'll talk about SQL injections. Of course, malware compromises the database server. It can potentially do pretty much anything, and then many other threats. And these hacks on attacks on databases of many kinds are extremely common, and seemingly only getting more common, especially on databases of particular sensitive types of information, such as credit cards, passwords, things that allow attackers to get information in bulk about a lot of different users, especially information that might allow them to leverage to further attack, to make money off of many users, or pull off identity theft or credit card fraud, or steal Bitcoin from wallets, or all kinds of things. So let's first look into the access control and security around typical database systems. So I mentioned where databases sit, and like any security critical component, they generally have access control, and that access control is basically is trying to ensure that only authorized users, typically only system administrators, can do certain things, can configure the database and that only authorized clients can read and access parts of the databases. And a very general standard principle that we need to think about whenever we're talking about access control is the principle of least privilege. So the idea that we should design user accounts and privileges to compartmentalize as much as possible, to define roles, different types of roles, so that each role has a very well-defined set of responsibilities, and we can define, well, which parts of a database, which database tables should this role have access to, and make sure that most of those roles do not have access to the most sensitive data or the privilege to change the structure of the database or to change permissions and things like that. So administrative access especially must be especially tightly controlled, because usually, once you have administrator privilege, you can give yourself permission to do anything else, and so that's extremely important. So it's also important to understand that access controls and protections apply at multiple different levels in typical systems. So there's typically access controls related to the operating system that the database sits on. The Linux or Windows server or whatever is going to have OS level accounts, and typically, in most database deployments, this is the operating system level accounts access control is used in a super coarse-grained mechanism. Usually there's a MySQL user or a quasi-user that the database server process runs as, that determines basically the permission of the database server. It, for example, gives the database server access to the server log files and the other things it needs to access. But if it's set up well, then the MySQL user on the database system should not have access to other arbitrary users files or administrator access or be able to do other things. And this can be important when that same physical server has other things going on that either other database servers or other non-database servers that might have different sensitivities. In other words, this is kind of coarse-grained compartmentalization. Another level is network level access control, the network firewall and port management policy. And this is because of the way the internet was developed basically separately from operating systems. The network level access control and policies is fairly orthogonal to and often not necessarily consistent with the with OS level access control, but typically there are controls on configure what ports the database can listen on for connections, whether it only listens from other processes on the same server, which is typically the safest. But if you're in a multi-tier web environment where the database server needs to be accessible for SQL requests and things from the logic tier processes on other servers, then of course you need to allow that kind of access. But if you care about security, you're probably going to try to use the network firewall and configuration rules to make sure that the database server cannot be accessed directly by someone on the general internet. So you should kind of at the network level make sure that the database servers are as compartmented as possible. Only the other machines that really need to talk to open SQL connections directly to the database server should be able to do so at network level, right? And then And then finally, the database, any modern database implements its own database level access control, where typically there are database level accounts and permissions where different users can have different rights on different tables managed by the same database process, right? And SQL has a lot of explicit commands. We won't go into the details, but if you're an administrator of a MySQL database, you can grant privilege and revoke privileges on objects such as database tables to particular users. And there's a variety of different privileges, for example, select means basically read. That's the way to read things from the database, insert, delete, update records, and so on, right? There's different ways to define access controls. So discretionary access control basically says that certain users are granted privilege to access certain types of objects. Role-based access control abstracts that a little one level further to say, well, we have many users, but some users can play certain roles, like a role of professor, or role of human resources, or a accounting user or something like that. And then you can grant or revoke privileges based on roles, and then declare users as members or non-members of a role. So just kind of a added level of indirection that sometimes makes user management more scalable. But of course, the fact that we kind of have, in typical systems, we have at least 3 fairly orthogonal types and levels of access control going on. There's the OS level access control, OS level accounts, like on the coarse-grained MySQL user. There's network level access controls, who gets to connect to the port, what port the database is listening on, and so on, and the database level access controls. This is, it gets pretty annoyingly complicated, and so mistakes are easy. And so we found that a lot of security vulnerabilities and breaches have come partly just out of misconfiguration. So the administrator didn't quite understand or think through the configuration clearly enough, and a very common failure mode is just neglecting to differentiate properly between normal user, database users representing standard, clients that just need to read and sometimes write things into the database on behalf of users versus administrators. And so if you just use one, you use the administrator account for all operations, then basically the tier 1 and 2 web servers that are going to be accessing the database will have basically administrator access to the database. And if one of them gets hacked, then the attacker can in turn get the entire database or control the database completely, right? So, and this kind of thing has unfortunately happened all too often. Okay, so so we want to, in practice, implement the principle of least privilege, in any ways we can. There are, it's often not trivial, and there are various ways to implement this practice. I won't try to, get into the intricate details. That's really the task that could be the subject of a whole network security course. But just to illustrate a couple of the standard practices, because at a typical company, there's a lot of workstations that, PCs, laptops that people bring in from outside, mobile devices that people bring in from outside And the company often doesn't have a lot of, only has a certain amount of control over the software on those PCs. Employees bring in USB sticks from the parking lot and plug them into their workstations, like we, saw in 2 lectures ago. So those, some of these PCs can easily get infected, or employees just get tricked, get successfully phished into disclosing their credentials or password or something, right? So often the huge number of PCs throughout the workplace building cannot be reliably expected to be fully secure at any given time because of all of those risks. And so a hacker that successfully infects one employee's workstation, well, that hacker is, the first thing they're going to do is say, okay, great, now what more sensitive information can we get? And they're going to go try to find the database servers on the network, and the servers where the real jewels are, and the real valuable stuff are. And so that's why in a well engineered network environment, there's got to be at least 2 different compartments, even within the behind the internet facing firewall, that's hopefully to whatever extent it can, protecting the whole company from the evil outside world. There's gonna be an internal firewall as well. That's going to protect other domains, right? In this case, we have 2 levels, basically. This intermediate level, the DMZ, protecting containing servers that have to be accessible from outside. And then the final tier of servers and PCs that are only typically accessible from inside. Let's see. I used to have another slide representing a more developed organization. What you really want is you also want to compartment the PCs from the database and other critical servers as well. So effectively, in a well-run environment, you effectively have multiple firewalls around different subnets, different categories of users and systems, to try to keep the database server and other critical servers accessible to as few other users and parts of the system as possible, right? So again, just principle of least privilege. I won't go through all of the specific. There are many kind of specific measures that are standard practice to take. Revoking unnecessarily privileges, just tightening up how a database server can be accessed and by what kind of users. Yeah.
Can you explain again why do we need the second firewall?
So I was unfortunately I was thinking this was a different figure when I was first explaining it. So this is a typical DMZ arrangement, demilitarized zone. So in this case, when an organization has some servers that need to be directly accessible from the internet, and of course many other servers like the critical database servers that should never be, have connections directly coming from the internet to the database server, typically we separate those into separate domains. The DMZ is specifically for the types of servers that need to be accessible both from the public internet and from inside. Things like mail servers, web servers, kind of connection, the company's public-facing web page, or the mail server has to be accessible from outside, under appropriate controls, so that mail can come in and web clients can come in and browse the company's web page and stuff like that. But you typically want to have a much more stringent firewall policy on the second firewall between the DMZ and the internal. So that you know, if, say, the web server or mail server get hacked, that doesn't automatically give the attacker the ability to get into the database server with the most critical secrets, right? I mean, it is bad enough if the hacker gets into the DMZ and takes over the web server or the mail server, but any kind of internet-facing thing that's you know, normally allowed access to the internet, supports access to the internet, is a bigger attack surface. You know, there's more chances that, you know, some attacker will be able to find a bug to exploit and get into that, than to attack directly from the internet into the, you know, most sensitive parts of the network, right? So it's just that kind of measure. Now, if the attacker does hack into the web server, the mail server, or something like that, of course, a good hacker, you know, concerted hacker is going to try to break through the second firewall as well, and there, you know, likely could be ways to do that. But, you know, a good network architecture makes that as difficult as possible. Make sense? Yeah. But the thing, yeah, the thing that, you know, this diagram unfortunately doesn't show is that there should also be, you know, firewalls, you know, between the database server, the subnet the database server is on, and the subnet, let's say PCs representing the ordinary employees are on as well. You know, you typically really want it to be even more compartmented, so that even a internal workstation with a USB drive compromised, you know, OS can't too easily be used to break into the database server in other internal compartments as well. Okay, makes sense? And of course, you know, this all the specific organization heavily depends on the organization, you know, the company, the structure, and, you know, I make no pretense that this is all the information you would need to be a, you know, good network administrator. There's whole books on that. I'm just trying to give you kind of a flavor of the types of, you know, practices and considerations that need to be implemented in order to keep databases and the data on them, you know, secure in the modern, relatively secure in today's environment. Okay? Yeah. Okay, so various host security practices, you know, configure the thing correctly. Think about, you know, the privileges in terms of configuration. You know, a good network administrator also worries about the physical security. You know, where does the server sit physically? I hope it's behind a locked door that not everybody in the company can get into, right? You know, so some administrators need to be able to get into it, but, you know, hopefully not just anybody. And so, you know, there are a variety of physical security provisions as well. You usually, sometimes it does happen that a, you know, hacker hacks a company by physically, you know, breaking in and carrying off servers. That actually does happen, although it's not the common case these days. So usually the electronic attacks are more common and more effective. Okay, so that's kind of the security of the environment the database sits in. So that's the first, you know, big thing to consider. But given that these databases typically have to be at least indirectly online, you know, in order to use a company to buy products from a company, you know, the user needs to talk to a web server that can browse the inventory and put things in the shopping cart and check things out and stuff like that. So so the database, at least indirectly, has to be exposed to user requests in some fashion, and many remote attacks come through by exploiting vulnerabilities in this path from otherwise legitimate users through the, you know, the presentation logic and business logic of the system to the database, right? And there's many different ways that can happen. I'll just talk about a few. So I mentioned earlier there's this common three-tier model for the way databases are often used. The presentation tier provides a nice website that users can where users can type things in a form to query the database, search for an item in the inventory or something like that, and then whatever the user enters in that form is going to get sent via HTTP to, say, a PHP script or a script written in one of many different scripting or other languages, right? And that's the web server implementing the logic tier, and then that is going to send SQL commands to the database server, right? Now, if we have correctly configured our network, the hacker on the internet is not going to be able to connect directly to into the database server. So let's assume that problem has solved. But here we're looking at attacks where the attacker can exploit the normal flow of events. And here, the example here is a simple SQL injection attack. So how many of you have seen or tried an SQL injection attack before? Okay, good. Yeah. So this is just a simple example where in a badly designed framework, you enter into a form, quote, and then some part of an SQL statement, and then it magically does something really bad, which we'll get into in a minute, right? So this is basically a way that the attacker can use normally allowed input channels to inject changes into the flow of the application to get improper access. So to look at this example a little bit more, let's assume that this application logic tier in the middle is a PHP script that's going to take the contents of that form and put the student ID field that the user enters into a SQL query, and then go submit that SQL query to the database, right? So this is a totally standard type of thing to do. Take input from the user, search for it in the database, in one particular field of the database. You have to construct an SQL query to do that, so you put the data from the form into that part of the SQL query, right? And so, yeah, so that's exactly what's supposed to happen. What could possibly go wrong? Well, so what can very easily go wrong is related to the way many of these scripting languages work. As any scripting language with $sign variables, like $ID, what that typically means in the semantics of these languages is take the contents of that variable, which is a text string, and drop it, replace $ID with the contents of whatever that variable means, and then reinterpret the whole string as code, right? And well, what went wrong here? What goes wrong is that if it's not properly quoted or sanitized, the contents of ID, what happens is the hacker can convince the script to where in the part of the script code where the SQL query is constructed, that SQL query template is often a quoted string. And so when the attacker enters that quote with some text, what they're doing is closing the quote that surrounded the first part of that query, and adding more stuff to the actual code, basically changing the code of the query in an attacker-controlled fashion, right? So in this case, the attacker is setting sets ID to not just, ID in this case is supposed to be a number, but the attacker, if the attacker can set it to one space union all number, blah, 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 then it's going to construct a query that has the attacker's additional code into it, which actually changes the semantics of the where clause. The where clause was trying to say, okay, let's just return the course and grade from the student ID of that student, but it changes the query to, return the entries for that student and all students and all entries from this other table of credit card information, right? So, basically dump the credit card table into the output that the attacker gets to see, right? So this is, just a, one simplistic but kind of prototypical example of the way an SQL injection attack, or one of the many ways an SQL injection attack can occur. Okay. So, and there's a simple solution to this, and the precise, best practice solution depends on what language you're working in, whether it's PHP or Perl or Java or anything else. But look up the correct standard sanitization mechanism to make sure that anything that semantically is part of this $ID can only be used as as something that's confined to that where clause and can't create kind of additional code around it, can't be interpreted as code, right? So in many cases, SQL injection attacks like these aren't quite so straightforward, because the attacker is trying to exploit existing authorized code paths and doesn't have the ability to doesn't necessarily have the immediate ability to change the code that the server is doing, and may not directly be able to see the output of the result. So often this logic server is doing one query and doing another query, doing a whole bunch of logic, in which the attacker can only manage to SQL inject into a form that goes in way up here, but the result of that, it doesn't immediately go back to the user, so the attacker can't directly see how that what that query resulted in, but instead it kind of goes down and does a bunch of other stuff before eventually going back to the user, right? And so it's it's often not quite that easy, but in cases where the query that the attacker has SQL injection capability on doesn't produce results that immediately go back to the user, one thing that that the attacker can do is turn it into kind of a yes/no question. Design a query that will basically test for the existence or test a yes/no question. Such as, am I in the database, or is the first character of, some variable, some information that I want to get, is the first character A? No. Is the first character B? No. Is the first character C? Oh, yes, the first character is C. Now I'm going to try doing yes/no queries on the second character. Okay, is the second character, are the first two characters AA? Are the first two characters AB, or sorry, CA? Are the first two characters CB? Are the first two characters CC? Et cetera, right? So smart attackers can get a huge amount of, basically unlimited information from yes/no queries that they get to craft. And often the only thing they need in order to get a yes/no query to work is just to produce any kind of distinguishable result, like the query worked or the query didn't work, the web page loaded or it returned a 404 or any kind of error. So just if the attacker can get the page to produce an error in one case for one answer to the query and some form of success, any form of success for the other answer, well, the attacker has a really nice information exfiltration channel, right? That can be used in all kinds of ways. So that's a very, very important standard tool. Another approach that, that can be even faster is to use different back channels. For example, an error channel. Some database servers were found to allow you to, so if you could inject, SQL inject something like a host name lookup. So a call to util inattr get host name, which is a SQL basically host name lookup function as part of a query. So we're selecting a credit card number from a credit card database in this injected code, and then sending it to get host name. Now, there's probably not going to be a host name on the internet, that happens to have the name of a credit card number for pretty much any credit card number. But it turned out that, well, that produces an error, and the exception, the error logic of this database was trying to be helpful, and it helpfully propagated the host name that it couldn't find back to the user in this error string, and so you get that string as convenient error output. And so the attacker basically gets a message back from the web server saying, that 16-digit number is not a valid host name, and the attacker goes, yes, I know it's not a valid host name, but it's exactly what I wanted, right? So yeah, and there have been variants on this kind of attack. The point is, and the point is not to focus on very specific vectors, but just to understand how many different types of back channels can be used to exfiltrate information if an attacker can find any way to actually inject kind of an attacker selected code. Okay. Yet another variation. Attackers are very good at putting evil web servers on the internet. And if you can get the persuade the SQL server to make a request to the evil web server, then then you can get the web server to basically deliver the secret data that you wanted straight to the front door of the attacker's evil web server where he's waiting for it, right? And even if the databases or this particular query that the attacker is trying to exploit is so locked down that the attacker can't even get the result of a yes/no query, say it always fails or always succeeds regardless of what the query did, but the attacker can just cause the query to take longer. Take significantly noticeably longer in the yes case than the no case, then the attacker can use timing as a side channel. And so anyway, so that's kind of a collection of different ways that many injection attacks can be used. The general point is it's really critical that in any part of the system where arbitrary input comes in from the outside, whether that's forms or other kinds of user interfaces, you always have to be super careful to make sure that's sanitized in some way and can't be exploited to cause attacker-controlled behavior. Okay. So, and actually, that's a perfect time to take a short break. Let's take a 10-minute break. So 5:10.